So this is C++ modules getting started today. This is supposed to be an introductory talk about modules. In particular, it's targeted at people who have never used modules before and are trying to just start out using the feature. You will not learn everything you need to know about modules here. There's a lot more than what will be covered in this talk. I will omit several things and simplify explanations to focus really on the things that I think are most useful to know when starting out. My hope is that this will be a good starting point from which you then yourself can dive deeper into the topic. We're going to focus on the mechanisms that are available in implementations today, which is named modules. We're not going to cover some of the more advanced features or features for which implementation support is still particularly bad today. I submitted this talk because I wanted to provide a good first talk to watch about modules that covers all the basics without assuming any prior knowledge. There are many excellent second talks to watch already out there, and you should watch them if you're interested in the topic. I will refer to some of them in this presentation, which I found useful, and you will find others online from other conferences and other places. So this is me. You can reach me through these channels if you want to reach out later. And let's dive right in with a very familiar example. So this is nothing about modules. This is just what we all know from C++, just header files and CPP source files. So typically, we split our code in such a way that the interface goes into the header file, the implementation goes into a corresponding source file. And then when a client wants to access the functionality that we provide, they include the header file, and then they can use the, in this case, the function that was provided there. So this approach has a bunch of problems that you're probably all familiar with. So the first thing is, because include is based on this very unstructured preprocessor mechanism, include can pretty much happen anywhere. It's not really bound by the structure of the surrounding language. So you might do something like this, where you want to define a function, and then just in the middle of the definition, you just put an include, and then it just pulls in some source code, and that gets just copy-pasted there. So yeah, you can put include in pretty weird places. People like to do this. There's actually some use cases where this can be really handy, but yeah, it can also be somewhat weird if you put it in the wrong place. So it would be nice to have something here that gives you a little bit more structure, a little bit more rules. Another common problem is that depending on what your header file provides, you may not be able to include the same header twice. That is why we need include guards in C++. And in this example, it's pretty obvious that we include it twice, but in real-world code bases where you have includes being pulled in transitively, it can very easily happen that you end up including the same header twice without noticing it. And then if that one provides, for example, something where the language says it must only be defined once per source file, then you get a compiler error. And when you see this for the very first time, you will be very confused. But yeah, that's why we have include guards. They're kind of a crutch, but they work. Another problem with include files is that they're not really surrounded from they're not really isolated from the surrounding state in the translation unit in which you pull them in. So one classical example is that you may have a class like this with a private function, and of course you all know how you can get to the private function. You can just define private to public, and then hooray, it's no longer private anymore. And people like to do this, for example, in testing scenarios where they want to do white box testing without weakening the encapsulation properties of the class. There's also other use cases like X macros. These are used quite heavily in system headers, for example, where it's just You set up some state, and then the header that you include actually depends on that state that was sent by the preprocessor before the include happened. Another problem is that include, like header files that are included don't need to be self-contained. The previous slide was an example of that, but a less evil example we see here, where we just define a class that uses a vector internally, but it does not, like this header file does not include vector itself. So this will work fine as long as our client looks like this, where the client includes vector first and then includes the header. Of course, if I now switch the include order in main.cpp around, then the code breaks, because now when the compiler encounters this definition for class A, it does not know yet about std vector, so I will get an error. And like these kinds of where you have these order dependencies and include files, that's also a common mistake that especially beginners run into very frequently. And then like after working with the language for a while, you just sort of adopt like all of these little techniques that ensure that you don't run into this. But the language doesn't really help you there, right? That's mostly like you learn from experience after like banging your head against these kinds of errors often enough. Then one other problem with the textual inclusion is one of efficiency, and that is often a concern with the big code bases where you have long build times. Because textual inclusion really just copy-pastes the code into the translation unit in the end. If you have like massive amounts of code in a header and you pull that into two translation units, then basically the same code has to get compiled twice. And that, of course, takes a lot of computational effort. And this problem of like build efficiency in particular is probably one of the main use cases why people are looking forward to modules. But modules actually help with all of these problems. And the reason that they're able to do that is really that they're just a much more structured mechanism than this textual preprocessor-based inclusion. They know about the rules of the surrounding language. And it's just, yeah, it just integrates much nicer with the other language features. So let's dive right in and look at a very simple example. So this is a very simple module. It just provides a single function. And we notice right away a couple of new keywords. So the first thing that we notice is that at the top here, we have this module declaration. This is something that, like, whenever you write module source code, you want the compiler to be able to tell pretty quickly, without having to parse the entire source file, whether it's a module source file or not. So we put such a declaration at the top before any other declaration to signify that this translation unit is actually a module source file. We also give the module name here, which is my_module in this case. Another thing that might be a bit surprising, especially if you come from other languages, is that the module name here is independent from the file name of the source file that provides the module. This is just like when the feature was standardized, it was decided that this is a kind of flexibility that we would like to have. So yeah, those names are completely independent. When you're on in the C++ source code world, then you really don't care about the file name at all. Only the module name is really what is interesting here. And you also notice that we put the export keyword on the function that we actually want to export from the module, so we have this sort of fine-grained mechanism for deciding which entities we actually want to export from the modules and which are private to the implementation of the module. If we look at the client side now, we see that we have a matching import statement that refers to the module by name. And then when we imported the modules, that gives us access to the function that was exported there. So as we said, the client can only see those things that were explicitly exported. So let's take a look at the different kinds of things that we can actually export. So we can export functions, as we've seen. We can also export types. We can also export templates. And here's another minor gotcha. If you're like me, you might be tempted to put the export on the second line of those declarations, so after the template angle brackets, because that's the place where we usually accumulate all of these keywords that we tend to write in front of declarations. But the export actually goes before the template angle brackets. And the way that I like to remember this is like what you're exporting when you're exporting things from a module is always names. You're exporting names. So the way that you introduce names in the language is a declaration, so export is always going in front of a declaration, right? And the template with the brackets, that's part of the declaration statement, right? So the export has to go in front of that because what you want to export is the full declaration. You can also export namespaces. That's a little bit weird because like namespaces are not really like other things that we define in the language. Really what this does is it's just a shorthand that says, okay, everything that is being defined inside this namespace block, I want to be exported so that I don't have to write export a million times on all the individual things. In particular, if you export, like the export only applies to this one block of the namespace. If you then go ahead and reopen the namespace in a different place without the export in front of it, then those things will not get exported. And that actually makes sense if you think that like, since anyone can reopen a namespace from anywhere, you really don't want them to be able to export the entire guts of the namespace just by having the export on there once. So yeah, this is really just a shorthand here, but you're not actually exporting the namespace. And then another thing where you can use it is with using declarations. So those can also get exported. And here, the important thing to keep in mind is that what the using declaration introduces is just an alias for a thing that was defined elsewhere, right? So the will be exported B function that we're exporting here still lives in namespace A, right? What we're exporting from namespace B here is just an alias to that thing that lives in this other namespace. And we will see later some examples where it's really useful to be able to do this, to like export something that actually lives in another place. Then another shorthand similar to what we had with the namespaces, we can also introduce these export blocks, where again, everything that is in the block will get exported. One thing to look out for here is if I put something in the block that actually cannot be exported, like in this case, it's a static function which has internal linkage, so it cannot be exported from a module, I will get a compiler error. So this is not dangerous. If you get it wrong, you will always get a compiler error, and the compiler will tell you that you did something wrong, but yeah, it's just something to keep in mind. And then finally, we can also export other modules. So here we have one module A that exports some things, and now from a different module B, we can not only import that module, but we can also do this kind of peculiarly looking export-import. And yeah, this looks a bit strange, but if you think about it a little bit, it makes sense. So in order to get access to the things that are provided by A, you have to import it. And now export-import simply says, okay, like all of these things imported from A, I now also want to export them as part of my own module. And to a client, the way that this looks like is now, if they import B, they can use the things that were exported by A without knowing anything about A, right? So it's exported as if it was declared inside B here. So one thing about exporting things that is a little bit surprising is that if something is not exported, does not necessarily mean that it's completely private to the module and nobody can get to it from the outside. In particular, there is a distinction here between visibility and reachability. And the export only really controls, like, is this name visible to people that import this module? But even if you don't know the name, you might still be able to reach it. So here's an example for that. I declare a class type, which is not exported, so it's private to the module. But then I have an exported function that returns an object of that class type. And now my client, if they call this function, they can store the return value. They can even reach inside the struct and access the members and call member functions and all of that. The only thing that they cannot do is they cannot name it, right? So if I try to name the type not exported from main here, that will not work. But I can, for example, use auto to store the return value here. And if this seems weird to you, then think a little bit more, because this is actually not new. You can do very similar things with auto return types already in the language. So here we have an example where we just return a function local type as the return type. Where you see this very often in the language is if you're using lambda expressions, for example, that you return from functions. There's even an instance where you cannot name the type because the lambda types are internal to the compiler, so you can't refer to them. But you can still hand such types out to your users. Then users just have to use auto to catch those return types. This is a somewhat subtle issue. It's, as I said, it's not new. It has been in the language before, but with modules, it becomes a lot more visible and a lot more important to know about these distinctions than before. Daniela gave a pretty good talk about this, the 3 secret spices of C++ modules at Meeting C++ Online. And if you want to know more, I highly recommend checking that out. Or since Daniela is actually at the conference, grab her in the hallway and ask her about it. She's definitely one of the most knowledgeable people about this. So let's look a little bit about the different kinds of modules, source files that the language allows us to specify. And I try to present them roughly in the order of usefulness. And this is not a complete list. Again, I try to focus on the things that are most important to know when starting out. So what we've seen in the examples so far is were all examples for primary module interface units. So primary because you can only have one of these for each module. And by default, you probably also don't need more than one. So unless you have good reasons for splitting it up, you will usually be fine to quite a large extent with just putting everything in the primary module interface. So yeah, it looks like this. You have the export module, and then you give the module name, and that's the signifier. That's what it looks like. And then yeah, you can actually put quite a lot of stuff in there before you will notice like a substantial negative impact on build times. But you might still want to split things up. In particular, if you're coming from like a header file, source file mindset, you might be tempted to like shove as much of the implementation details into a different file. This is not required to the same extent as it is with header files. Like you don't have these problems that if you put certain definitions in the header files, then they cannot be included by more than one source file. But you might have other reasons why you want to split this up. In particular, if you think about optimizing rebuild times on your code, you might want to put like all of the stable parts of the interface into the primary module interface, and then put the implementation details that are prone to change much more frequently into an implementation file, so that when you make changes to the implementation, you only need to recompile that one source file, but you don't need to recompile the source for the primary interface, and as a consequence, you also don't need to recompile any of the clients that are consuming this interface. So in those cases, it's very useful to be able to make the split. The signifier here for the implementation source is that it does not have the export in front of the module declaration. So it's sort of just extending this module that was defined in this interface file. And the crucial limitation here is that you cannot export anything from the implementation unit. So yeah, this line here, that's the signifier. You might want to go one step further and instead of just splitting like into interface and implementation, you might also want to split the interface into different components. And that's what you can use module interface partitions for. So here our module is called mice, and I want to split the interface up into two parts, Pinky and the brain. The way that this works is so the primary module interface always needs to provide the full picture, right? So if I have module interface partitions as part of the module, the primary module interface is required to export all of the individual partitions and list them. And that is actually your responsibility to get that right. If you mess that up, if you forget one of the interface partitions, your build tool is not required to complain to you. But then if you split it up like this, so first of all, you can partition your interface this way. But what you can also do is define private parts like the secret master plan that we have here at the bottom, which will not be visible outside of your module. So the thing here is that so outside entities can only import the primary module interface, right? They can only import the mice module that is defined at the top, but they cannot import any of the individual partitions. So they will actually never be able to see that there is a secret master plan in there. But the individual partitions that belong to the same modules, they can import each other, and to them, this will be visible. An interesting question is now what would happen if the Pinky partition would also define its own secret master plan. And this is actually allowed. So in old C++, in the pre-modules world, that would probably be a one definition rule violation, since you have two entities defined with the same name. And you wouldn't get a diagnostic for that unless you got lucky. The cool thing about modules is that you're still not allowed to do this, but the compiler is now actually required to diagnose that and give you a diagnostic. The rules are the same as with the one definition rule. If both definitions are actually the same, then you're allowed to have them twice, right? But if they're different, then you're not. And if you try this out with Clang, and you define like 2 different structs in 2 different partitions with different content, it actually tells you exactly why they don't match and where the difference is between the 2. On MSVC, I think this is still not implemented correctly, so they will just roll the dice and pick one at random, and yeah, so be a bit careful there, but hopefully they will fix that before long. Yeah, as I said, remember to export everything from the primary module interface. That's very important. And yeah, you can keep stuff secret. There's also another form of module sources, which is called header units. I'm not going to talk about them today, mostly because I don't think they're mature enough that you should start using them without knowing a little bit more. Daniel Russo gave a talk last year at C++ Now, explaining like some of the difficulties why these are more complicated for implementers to implement correctly. His talk was pretty pessimistic. I think the tooling community has been gotten a little bit more optimistic again as to like how to solve some of these problems that he's talking about. But yeah, check this out if you want to know why header units are difficult. And also, if you want the full list, like all of the other types that I skipped here for brevity, Daniela again has you covered. She has this nice table in almost all of her talks about modules. This one is from her NDC Tech Town from last year, which I think is the most recent version of the table. Yeah. So yeah, check that out if you want to know more. Let's switch gears for a bit now, and let's actually talk a little bit about build systems here and compilers. Because if you have been following along with modules for a while, then you probably know that like compilers started having support for modules to some extent pretty early, but build systems have generally been lagging behind by a lot. And a lot of people have been wondering like why that is. Like what are we waiting for? Why is this taking so long? In this section, I want to like not only explain how you can use CMake to build modules, but also explain a little bit about why it took so long, what's so different there for the tooling. So again, the old school example here, this is how you've been doing stuff in CMake for a long time, how many of you are probably still writing CMake today. You declare that you want to build some code, and then you have this target sources command where you just specify all of your source files. And with header files, you can just give a list of all the header files. It doesn't have to be structured, just a flat list. But really, if you don't want to, you don't have to. This is mostly to keep your IDE happy so that it displays all of the source files. But to make a compiler, really the only thing that you need is the correct include directories down here, right? And then the compiler will be able to find the header files. So one thing that I want to talk about first is if you're still doing things this way in CMake, let me tell you about a new feature that was introduced with version 3.23, which is called file sets, and which you should be using instead because they're awesome. So with file sets, what you can do is in your target sources command, you can have a separate section, which you prefix then by file set headers. And you put all of your header files in there. And then you have this nice little option called base directories. And where before you would use the target include directories command to specify the include directories, you now can put this here in the base directories. And this solves a bunch of issues in CMake that were pretty awkward before. In particular, installing this target is now a lot more nicer, and you cannot get these weird conflicts anymore between like build tree and install tree paths that might be conflicting. If you ever ran into weird stuff like that, that's all solved by this. It's just a strictly better solution. So if you're not using it yet, and your CMake version is late enough, then switch to this. It's great stuff. So why am I telling you about file sets? Because That's also what we use for modules, right? So yeah, modules obviously only work with C++20 code. So we're setting the language version here. And now in the target sources command, if we're at least on version 3.28, we now have this new file set type called cxx modules. And now we can put all of our module source files in there, and things will just work. The caveat here is you should really be using the latest tools. Try to use the latest CMake as you can. This is still being developed very heavily. You need at least 3.28. If you want to use the modularized standard library, you need at least 3.30, although it's still an experimental feature in there, so I'm not going to talk about this today. There's a talk by Bill Hoffman from CPPCon this year where he talked about this. There's also a blog post on the Kidware blog where they talk about this feature and why it's still experimental, what to watch out for. And yeah, with your compilers, try to have the latest as you can. Visual Studio needs at least toolset version 1934. Toolset version, that's the version that the compiler prints out when you invoke it, right? So if you call CL in the build shell, or if you look at the compiler's output in the Visual Studio output window, this is different from the Visual Studio version that you get if you click on like About Visual Studio in the IDE. So yeah, this is the toolset version. If you're not using Visual Studio and MS Build, you need to use Ninja. CMake currently doesn't support other generators, like Makefile generators don't work with modules yet. And with Ninja, you also need the latest version. If you're using Clang, Clang introduced the module support with version 17, but it was very buggy. Try to go to 18 or better 19. GCC introduced module support with version 14, which was released this year, I think. So it's pretty recent, but it still has a lot of bugs. So try to go, like if you can be on trunk, try to go on to trunk with GCC. Like GCC is the least mature support from these three. Even with the latest tools, there's still bugs. So yeah, be a bit cautious there. But in general, like the support is good enough that you can start using it, right? It's not like it breaks at every corner. It's just you have to watch out for a few things, but don't be discouraged to like not use it today because like most of the essential things are there. A few things to keep in mind. So one thing is like when is a source file actually a module source file, right? When should I put it into this cxx modules file set in the CMake file, and when does it just go into the normal source file section as before? And the simple rule here is if there's an export module somewhere in the source code, it's a module source file. If it's a module partition, it's a module source file. Otherwise, it's just a regular source file. In particular, if it's just importing stuff, but not exporting, it's not a module source file. If it's a module implementation unit, then it's also just a regular source file. And if you get this wrong, then your compiler will throw weird errors at you. Another question that you will probably come in contact with quite early is which file extension to choose. When the feature first started appearing, compilers started introducing loads of new file extensions, usually all incompatible between different compilers. So yeah, here's some examples for what we got there. By now, things are starting to get mostly uniform, like at least Clang and GCC seem to agree on like which file extensions to treat as modules file extensions. GCC seems to have settled on the notion that they just don't care about file extensions at all, and they want to leave all of this up to the build system, which is probably what you should do as well, right? So if you're using CMake, you're not required to use any special file extensions, right? You can just stick with .cpp or whatever you were using before. And I think that that is probably the best way to go, because the problem is if you are using these special extensions, you should only be using them again for what qualifies as a module source file above. Otherwise, your compiler will treat the source as a module source, and you might again get weird errors. So my recommendation would be to just stick with whatever file extension you had before. I'm also using .cpp in all of the examples here, and only make the distinction in the build system. So, speaking about build systems, what's a build system anyway, right? Why do we need build systems, right? We all know how to compile stuff, right? You can just invoke the compiler. So why bother with a build system? So really, in the end, what a build system, its main responsibility is, it's a dependency tracker, right? I have this source file. It depends on a bunch of header files, which again might transitively depend on other header files. And what I want to be able to do is, if I make a change to one of these files, I want all of the affected source files to be recompiled, right? If I recompile too little, if I missed some dependency, then my program ends up in an inconsistent state, which is very bad. If I recompile too much, it's not quite as bad since my program is still correct, but I'm also doing a lot more work than I should do, right? I want my builds to be efficient, so I don't want them to rebuild stuff that doesn't need rebuilding. So the build system stuff really is to keep track of all of these dependencies, and then if I do an incremental rebuild, be able to figure out for me what is the exact set of source files that need recompiling. And this analysis of the dependencies and whether a source file was affected by a change is something that can be done in parallel for all of the source files, right? This is an embarrassingly parallel problem. I can just, invoke whatever tool does this for each source file, do that all in parallel, and there's no interdependency here. So how does the build system know which source files need rebuilding if, for example, I touched one of these header files? Well, the easiest way is you just tell the build system by modeling everything explicitly. And some projects still do that to this day. This used to be the only way to do it for a long time in the past. You just tell in the make file what are all of the sources that are depend on both CPP and header files, right? And you have to list that for all your files, right? This works, but this is probably not what you're used to today, right? What we want to do is, as we saw in the CMake files, I just give a flat list of these are all the sources, these are all the header files, you figure out the dependencies, right? And that's what we want the build system to do. That's what we expect of it. So how does the build system do this? Well, it asks the compiler. So for example, if you invoke GCC with this -M flag, it will actually write out such a dependency file, which contains a list of all the headers and the sources that were pulled in here. So if we think of the compiler here as part of a build pipeline, really the inputs into the compilation process are all the source and the header files, and there's two outputs. There's the object file, which then later gets processed by the linker, and there's this dependency file, which if you're not a build system maintainer, you probably didn't ever have to look at, but it is an important output artifact here for ensuring the build consistency. So inputs, outputs to the linker, and this dependency file. So what changes now for the build system if we move from a header world to a modules world? So the most obvious change is that now my dependencies are not just header files, they're also source files, which means these are also files that need to get compiled on their own. So if we look at the compiler now, what changed is that the output that is produced here by the compiler is next to the object file that gets passed onto the linker. We also produce what is called a binary module interface, and so this is not actually called .bmi on most compilers. That's just like, it's called the binary module interface. And this contains then all of the information that sources that depend on this module need to have as inputs to their own build process, right? So BMI files produced by compiling one source file are needed as inputs for other source files that want to import this module. That's the big change here. And the implication then is that where before we had this embarrassingly parallel world where all of the source files were independent, we now have dependencies between source files because of these binary module interface. And that's the major change. Like, that's something that build systems did not have to worry about before, but now they need to. And like, what the build system needs to ensure is that if there is such a dependency, that the source file that provides the BMI is actually built before the source file that wants to import that module. And the way that the build system achieves this is they compile every source file twice. So if you look at the build output from a module's build, you will see that there's a first build path, which is still embarrassingly parallel, that just scans for all the dependencies between the source files. And only then, in the second phase, is the actual building that also produces the object files, which then respects this order introduced by these dependencies. So in CMake, we still want to have the flat list here, but in the build system view, we do want to have these inter-source file dependencies managed, and then if one source file changes, then of course these dependencies transitively apply also through the BMIs to the clients of that module. Okay, so much for build systems, just as a quick explanation for like why things are different now, and like why it's not just a trivial like putting one additional option on the compiler invocation, but why this actually requires more work. What I want to use the remainder of the time for is to actually give some useful advice for like, if you're first picking up modules, you now want to write like some real code, not just toy examples. What are some of the problems that you might run into, and how could you deal with them? So in a perfect world, you could just, once you start putting up modules, you just never use includes again, right? Everything's a module, everything is great, right? Only use import, no longer use include. Fine, but that's probably not how it's going to work, right? For a considerable time, we will have to live in a world where like modules and header files have to coexist, right? We can't just change everything overnight. And if you just declare a module right now, like this right now, and you just put an include where we have the import right now, that will probably not work. Because there's just too much stuff going on in a header file that doesn't really work well with the module mechanism. So what we can do instead is we can use this new syntax that we haven't seen before, where we just, instead of having the full module declaration at the top of the source file, we just say module semicolon. So this just tells the compiler, hey, there's a module in here, but I'm going to do some other stuff before I actually show you what the module is. And then, in between these two, that's where you put that's where you can put your header files. And this region is also referred to as the global module fragment of the module source. And what's going on behind the scenes here is really that everything that you put in there is interpreted like as not part of the module, right? This is still, so if you, the way that the C++ language just distinguishes this, there's like the global module, everything that you don't put explicitly as part of a module that you named is implicitly part of a global module, right? So all of the C++ code that you were writing in the past before using modules, that all lives in this world of the global module, right? And if we put things here in this global module fragment, what you're saying is this is code that lives in this world, right? In this old world that exists outside of modules. And then everything that happens down here, the green part, that is usually referred to as the model purview, this now lives in this new world of modules, and it follows the new rules. The problematic cases are now where these two worlds start to collide. So as long as you have things always live either in the old world, in the global module, or in the new world where they're attached to some module and defined in some module purview, that's fine. But if you have the same entity appear in both worlds at the same time, things get weird. So, for example, let's say I have a module like this, which it imports the standard library as a module. It exports a function that returns a string. If I import this module, I have the issue that we saw before, where I can call the function and I can catch the return type, but I cannot name it, right? Because the name std string was not exported by my module. So this code won't compile because it, like, main will not know the name std string. It will just say like undeclared identifier or something like this. So you might be tempted, and your muscle memory will probably strongly tempt you to just write include string. Because yeah, that's it, like the string header, that's where this name comes from, right? But this will not work. And the reason why is that if names are exported from a module, they become attached to that module. And you can actually observe that by using the bin utils here. So if you just compile like this source code into a library, then you use nm to look at the symbols that actually provides then as part of the object file. You will see the mangled name here. You can unmangle that with C++ filth. And then you will see, okay, yeah, that's just exporting a function, the answer, no surprise here. And then if you put that function into a namespace, you will also see that the namespace becomes part of the mangled name. And also, like if you change the signature, if you add parameters, they also become part of the mangled name. The return type is not part of the mangled name in C++, right? That's one of the reasons why we can't overload based on return types. Now, this is all old stuff, right? This is just how the linker resolves names between translation units. But let's look now at what the names are, how the names change if we put the things into a module. So first we get a new symbol that we didn't have before, but if you look at the last line here, you will see that the function name now actually got this at my module attached to it, right? And this is something that was not in there before. You couldn't get mangled names like this before. And this is what it means that the name becomes attached to the module, right? So on the C++ like name lookup level, the function is still just called the answer, and it still just lives in the global namespace, and that's how it can be found. And nothing changed about this. But now the build tool also has this information that, hey, actually this this definition actually comes from this module. And that is not something that we had before. And having this information available, even if it's not taken into account by the language for name lookup and so on, can be really helpful. In particular, if you think about if you how a compiler would diagnose things like ODR violations, right? Like one of the reasons that we can't do that in C++ before modules is because we don't know where the definition comes from, right? So it's very hard to say like if two definitions come from the same place, then yeah, they're obviously the same, right? But things get difficult if they come from different places, and this can help you with that. But since it's this new kind of concept, this attachment that we didn't have before, it also can lead to these surprising effects, where if you get the name from two different places and it ends up being attached to two different modules, then even though it's the same name on the name lookup level, it's not the same thing, and the compiler will shout at you. So how can you mitigate this? Without getting into all of the technicalities here, like some simple rule of thumbs. When mixing imports and includes, try to always put all of the includes first. That's just a good guideline to follow. This should actually work for the standard library. That's where the standard guarantees it. It's currently not guaranteed for any user code, but this is an area that is still somewhat in flux, and depending on how tools are able to mature here, we might be able to have that as a general guideline. It also might be that tools get smarter and the order does not matter as much at some point, but for now, I think this is a reasonable guideline to follow. Another good hint is to always to include the standard library early. So, for example, if we have this thing here where we have a library, this is a library that does not know about modules, and I want to modularize it, right? The simplest thing to modularize is to just have a new module and just put the whole library in the export block, right? But this, in this case, is problematic because part of the library is also the string header from the standard library, right? And that is definitely not something that I want to have in the export block, because then I get exactly the problem from before, where now the string suddenly becomes attached to the library lib. So a trick here is to just include the standard library header before the export block. Because if you think about like what happens in the compilation of libm, this still follows the normal rules of compilation. We include the string header as part of the global module fragment, right? So the string name becomes attached to the global module as it should. But now, when it ends up on the include HPP and then the include string there, it hits the include guard for string, right? Because it already has been included. So I don't get any of the standard library stuff in my export block. So that's a pretty neat trick of like filtering out dependencies that you don't want to end up in the context of your export. Another trick that is a little more advanced is we talked about using before, right? So export using is exporting a declaration to a thing that lives somewhere else, right? And we can use this here where the awesome type that we pulled in through this library header lives in the global module fragment. I cannot export anything from the global module fragment, but I can export the alias from the module, right? So export using is that's a big use case for this that we didn't have before. One thing to take care, you really should fully qualify the name for complicated lookup reasons that I don't want to explain, but yeah, just take it as a guideline. Always fully qualify the name if you do this. But then it's a pretty powerful trick. Also, somewhat similar situation. You have a declaration in the global module fragment, right? This is great because it doesn't get attached to any module, but you can't export from the global module fragment. In the model purview, you can export, but declaring it attaches it to the module. What if you need a mixture of both? What if you want to export without attaching to the module? Can you do that? And the trick here is to use extern. If you export an extern C++ declaration, that means it gets exported but not attached to the module. If you want to know why this works, again, Daniela has talked about the gory details a lot more than we have time for. Really quick before we wrap up, one thing is that you cannot export from modules is everything that has to do with the preprocessor. This is a feature. So if you have preprocessor stuff in your library that you want to export, you need to either ship a header file along with your module, and then you just put all of the preprocessor stuff in the header file and everything else into your module source file. So you have to split it up. Or if you can, just replace all of your preprocessor thing by like proper language facilities, which you can then export properly. But this, like whichever you choose, if you have preprocessor stuff in your library, you need to think about a little bit how you want to do this. Again, Daniela gave an excellent talk at CPPCon 2022. And I want to call out like not only the talk itself, but also the GitHub repo that comes with this talk, because in there she modularized a couple of existing libraries that were like legacy libraries, which she then modularized, and where she demonstrates like a bunch of different techniques that you could run into if you want to bring legacy code into a modules world. And yeah, it's really insightful to see this in action, what you can do there if you run into difficult, tricky situations there. So highly recommend it. Wrapping up. So modules are slowly maturing. I really encourage you to try them out today. Like, don't be discouraged by all of the pitfalls. Yeah, there's some new things to learn. There's still some dark corners that are a bit scary. But the more people use it, the quicker those get fixed, right? And right now, I think one of the main problems of the feature is that not enough people are using it. So that's why the fixes also take longer. Especially if you want to integrate header-based legacy code, there are some challenges, but there's also a lot of techniques how to deal with them. And lastly, I think we have a really unique opportunity here in that like modules really have the potential to change a lot about the ecosystem, in particular the tooling ecosystem. So especially if you're a young developer, right, and you always wanted to like get started in working on tooling, working on build tooling, on build systems, on compilers, writing like a new build tool that would just make everybody's life better. This is the time to do that, right? We have some really low-hanging fruit there where there's incredible opportunities to build really useful stuff with very little effort. So I would really encourage everyone, like look at the feature, look at like the new opportunities that it provides, and if you see something interesting, just play around and try to write some tools. If you want to go from here, here's some references to other talks and articles that you can look at. And lastly, I have a little Godbold example with like a minimal Hello World example that you can then extend to just start playing around with this and try out some stuff. Thank you. So we are on time, but if we have one or two quick questions.
Thank you very much for your talk, Andreas. I have a question from our online track. Honey Sukasons asks a dumb, very late question regarding the name modules. I don't know where they come from, but isn't module conventionally used for the different logical components in software? What might be the reason the same name is adopted for modules? Would it be nice to solve this ambiguity?
I'm not sure it's necessarily an ambiguity, right? They're still a tool for logically structuring your code base, right? And partitioning your code into different logical components. So yeah, they work slightly different from modules in other languages, but I don't think it's a misnomer. I think it's, yeah, I would say I disagree with the premise of the question.
And a very quick question from Gregor Kvass. He asks, are there any plans for the standard library to be fully modularized?
Yeah, so this is actually in the standard in C++23, and we even agreed to retroactively apply this to C++20. So as far as the specification is concerned, yes, it's there. Tools are catching up. Details in like Bill Hoffman's CMake talk. Yeah, it's a bit difficult technically, but we want to get there. Yeah, maybe one or two more questions because I think the next speaker needs to set up then. Yeah.
Maybe to confirm, I did try out modules a few months ago, and I had the primary module file and another source file, and an exported and a non-exported function in both cases. And in all four, I saw that everything gets recompiled when I change the definition of the functions. Is that what I'm supposed to see?
No, if there's no changes to the interfaces in the primary module interface, then you shouldn't have to recompile clients that just import the primary module interface.
Okay,
maybe you found you hit upon a bug in your tools there. Yeah, but it's supposed to be isolated in that case.
So it's supposed to behave as if the implementation was in the CPP file and.
Yeah.
Okay. Thank you.
Then one last question, and then feel free to come to me afterwards if you have more. Yeah.
Just a quick question.
Sure.
Regarding the mangled names, which you showed on slide 41, you said the module name is always mangled into this mangled name, always there. Is that really true, or does it depend on the toolchain? Because I thought it's only for the Visual Studio toolchain and not the other ones.
If you go by the letter of the standard, it doesn't have to be, right? The standard has these two models, like the weak and the strong model. So in the past, there was disagreement whether it's really a good idea to always have this mangled in. By now, the consensus seems to be that you always want the strong model, it's strictly better, and that's also what all of the implementations are now converging on. But the other thing is still in the standard, and there's no proposal yet to remove it. But if I had to guess, I would expect this to become deprecated eventually, because now the tools are all moving to the strong model.
Okay, thanks for clearing that up.
Of course. Then let's wrap up, and I'm happy to talk to you offline then. Thank you.